In this lesson, we're going to cover Kirchhoff's voltage law and current law. All right, so right now we're going to do voltage law, and here I have a lovely circuit. Let's suppose this here is your battery, and we'll do the standard 3 volts. And these are resistors or light bulbs, let's say. We can make them into light bulbs, whatever you like, or resistors. And let's pretend that all 3 resistors or light bulbs are identical. So 3 identical light bulbs or resistors. All right, perfect. Right now, this is called a series circuit. So remember, a simple circuit, you'll only have one resistor or light bulb and then one battery. Well, this here's a series, and the reason why they're called series is because you've got 3 light bulbs in a row or 3 resistors in a row. Series circuit. Another way you can tell that this is a series circuit is because the electrons have no choice but to go through all 3 light bulbs. So if I were to draw a path for the electrons, remember this is electrons, not conventional flow. It comes out of the negative terminal and through the resistors, and they are forced to go through each resistor and then back to the battery. Okay? So electron flow. Perfect. All right, so what does Kirchhoff's voltage law say? Well, basically, any net voltage in a closed loop is equal to 0. So net voltage is equal to 0 in any closed loop. Okay, so in any closed loop, that is the general rule. So what does that mean? Well, this here is a closed loop because once it goes back to the battery, then it just continues on the same path. All right, so you can say same path and it's closed, it just repeats itself in a sense. So essentially what's going on is this battery is a voltage gain of 3 volts. And because all 3 light bulbs are identical, this here is a voltage drop. And because they're identical, you're going to, or the electrons will give off 1 voltage for each light bulb. So this is a drop, and a drop. So in a sense, you can say this is +3, then -1, then -1, then -1. And so the net voltage will be 0. And so that's how you know how much each light bulb in this case will have. In this case, all the light bulbs will have the same amount of brightness. Hopefully this is sort of a trigger or a reminder of what you learned in grade 9 electricity. All right, let's try a parallel circuit. So this is a series circuit. I'm going to show you an example of a parallel circuit. So this here is a parallel circuit. So again, you have the battery, and then you have 3 resistors or 3 light bulbs. All right, you can turn them into light bulbs if you like. The difference in this one is that each light bulb or each resistor has its own path. Okay, you can also redraw this circuit to look like this. And I'll show you in another drawing that could look similar. You can draw it like this, for example. So it has 3 branches. And here's one resistor, the other resistor, like so, and then back to the battery. All right, so this diagram is similar or the same as this diagram over here. Okay, and the reason why we do that is there's a big assumption. We're assuming that there is no resistance in the wire, but in reality there is. In real life there is. Okay, so these two are very similar. If you want to write that down right here, like so, these two these two circuits are identical. Okay, and why? We are assuming the wires have no resistance in them, or very little that we don't need to calculate. Okay. All right. So let's get back to this circuit over here, because this is your standard circuit. Everything likes to be, in squares or at right angle triangles. I mean, you do get circuits that have diagonals as well, but most diagrams, they try to square all the wires off like so. Okay. So you have, let's say this is 3 volts, and remember Kirchhoff's voltage law is that for any closed loop, the net voltage is equal to 0. So let's first do our loop number 1. Okay, I'm going to do electron flow, and here's loop number 1. I'll do it in red. So we're coming around, and then you have something called a junction. Okay, this here, the electrons have a choice. They have a choice to go on, or like to the right or down. Okay, and so this here is your junction. And so let's continue on this path, and let's say this is the first resistor, and then back to the battery, okay? And so that is one full loop, and because of Kirchhoff's law, this here is going to be taking up 3 volts of energy, okay? Let's do the next loop. I'm going to continue, same thing. I'm going to do this in a yellow color. At the junction, it's going to go by. There's another junction over here. Okay, it will have a choice, and it will go down through this resistor and then back like so. And so this will also take 3 volts. So I'm going to write this in red so you can see 3 volts. And the last loop, as you can tell, is also 3 volts, because that is also another closed path. Okay, so if I do that in blue, for example, this is the other path. Now, what kind of circuit is this called? This is called a parallel circuit. Parallel circuit. And you can see the resistors are arranged such that they're parallel to each other, and that's why they call it a parallel circuit. All right? So each loop will have a net voltage of 0, so each light bulb will also have the same brightness, but they'll be brighter than actually this one, 3 times brighter, because each bulb here would be a voltage of only 1, whereas these ones are a voltage of 3. Now let's go back to the other drawing. If it was the other drawing, it doesn't really make a difference. So again, this would be 3 volts each, because if you draw the path, here the junction actually is right here, okay? And you have the choice of 3 different options for those electrons, but the same thing as well over here. And the reason why is, again, the wires, we do not have any resistance in wires. We're assuming that. And so the electrons technically have a choice to go through this one, or that one. Some of you don't like this parallel drawing setup, so if you want to redraw it, you could redraw it like this if you like. All right. But again, this here is path 1, for example. And then the second path here in the yellow through the middle one. And then the last one, I'll make the blue one here, like so. And it's the same thing, essentially. All right, now that we've done the voltages, there is another law called Kirchhoff's current law. So here we are. We We have Kirchhoff's current law. Conservation of charge. That is essentially what Kirchhoff's law is. So, in other words, you have this loop, which we call a branch, and the current remains the same through the entire branch or the entire loop like this. But we technically are going to say branch because I'm going to show you where the difference between a loop and a branch later. All right, so current remains the same throughout the entire branch. So what is a definition of a branch? Essentially, it is from junction to junction. There we go. So from junction to junction. Now in this example here, it's a series circuit. There is no junction. So in this case, the whole thing is one branch. So remember, we're talking about charges, so electron flow or current flow. So we don't care really what the energy is, which is, the 3-volt battery, but instead we care more about the current or how much flow is going out of the battery. I'm going to draw electron flow again, and let's pretend that we have 1 amp flowing out of this battery. Now, that's actually a lot. In real life, they're on a scale of milliamps, but instead of having all these strange decimal places, we're just going to deal with nice round numbers. And so in this case, the flow is 1 amp, and it's going to go through this resistor and this resistor and this one as well, and back to the battery. So the flow does not change, and it remains the same throughout the entire branch, okay? So let's do an example where the flow does change, all right? So in this case here, we actually have 2 branches. So how do I know? Because there's a junction here and here. And technically, there's actually 3 branches. So remember, a branch is from junction to junction. And so when I say there's 3 branches, there's this branch over here, there's this one over here, okay, and then there's this one over there. So there's 3 branches because there are 2 junctions. And that's basically how you define a branch. Although the loop, according to the voltage law, this is a loop and that's a loop, okay? Technically, this is also a loop as well. So 3 branches and 3 loops, I guess, with the 2 junctions, all right? So let's pretend that these 2 resistors are not identical, all right? So the resistors are not identical. So in other words, one branch is going to suck up more energy or will require more electron flow than the other, okay? And so let's pretend we're going to have 1 amp again, and it's going to hit this junction. Now at this stage, the electrons have a choice. They could either go down or to the right, whereas in this series circuit over here, there is no choice, right? So remember, this is your series circuit, series current or slash circuit, and this here is your parallel circuit. Perfect. Okay. So here, I'll have a choice. Now, typically, if the resistors are identical, then they're going to split up 50-50. But because they're not identical, and let's suppose that this resistor allows for more electrons to flow. And let's pretend it allows a lot more, like 80% of it. So that means 0.8 amps of flow going through here. All right. In this branch, from this junction to this one, this whole branch is 0.8, which means if I were to figure out the flow of this other branch, denoted in the greeny blue color, that means it'll be 0.2 amps. It cannot be more than 1. So basically 0.8 plus 0.2, the combination of those two cannot be more than 1 amp because that's the flow. This is the maximum amount in a sense. All right, conservation of charge means you can't just make up more electrons. It has to be equal. All right, so we have this junction here, 0.2 all the way. This junction is 0.8, and then when they combined over here back to the battery, it'll be 1 again. So let's fill out the colors. So between this junction and that junction, that's the other branch, that's 1 amp. This junction to this junction is 0.8. This junction to that junction is 0.2. All right. Another way of thinking about Kirchhoff's current law is what goes into a junction must come out of a junction. So what goes into a junction must come out of a junction. That's another way of looking at it. So I'm going to look at this junction right here. I'll just highlight it like that. Okay, and I'll bring it down here so we can analyze that. All right, and I'm going to redraw this junction. So I'm going to redraw it like so. Okay, so remember you got 1 amp coming in. And basically this one in the green was 0.2, this one in the red was 0.8, and this one was 1 amp. Perfect. So this here is the junction of interest that we are looking for, and what goes into the junction must come out of the junction. So if I actually sort of draw the junction like this, or cut it or slice it like this is my input and this is my output. So this is what is going into or input into the junction, and this side is my output. Okay, output or out of the junction / output. So there you have it. Kirchhoff's current law. Again, what goes into the junction comes out of the junction. So in other words, 0.8 plus 0.2 will equal to 1 amp. And then don't you have Kirchhoff's voltage law, which is right here for any net voltage equals to 0 for any closed loop. All right. Next lesson, we'll go over equivalent resistance and Ohm's law, and then we'll be ready to solve for circuits. See you then. Bye.